Alright, grade 12 chemistry. Let's get started on this one. So today we're talking about enthalpy and entropy and where the energy for chemical reactions actually comes from. So really our main thing here is the bond energy theorem. We're also going to take that and turn it into potential energy diagrams because it's a very quick way to visualize energy changes in a chemical reaction. And you'll be seeing a lot of them. So good idea to have a look at them. So let's get started with a little bit of slightly more advanced thermodynamics. One big thing, just keep it in mind up here, we're going to ignore entropy or entropic changes when we do problems, when we do calculations, but be aware that they exist just because some of you might end up in a analytical chemistry class or a thermochemistry class at some point. And that does become very important because there are certain reactions that look like they should occur, but they won't because of entropic effects and various other interesting things like that. So we've got these three quantities of energy that we want to talk about. We've already talked about enthalpy, which is heat. And that's where we get endothermic, exothermic. It's on the delta H value. So endothermic and exothermic is only referring to one type of energy, if we wanted to kind of simplify it that way. We also have entropy, which is disorder. And that one's kind of hard to explain. Entropy is very hard to explain. We literally do mean disorder when we talk about entropy. So, for example, this piece of paper, right? It's a square. It's all together. The chemicals are in long strands and everything. If I were to rip it up, if I were to rip up the piece of paper and make confetti out of it, it's still all the same chemicals, right? It's at the same temperature, so the enthalpy hasn't changed. The enthalpy hasn't changed. But the entropy has. We've increased the amount of entropy by ripping it up into tiny chunks. Same thing with this water. The water in my cup here is liquid water. If I turn it into a gas, it's still H2O. It's still hydrogen and oxygen bonds, but it now has more entropy as a gas than it does as a liquid because the gas is more disordered. It's all over the room instead of stuck in this cup. So that's entropy. And then Gibbs free energy is the energy available to do work. It's actually defined mathematically as the when we want to change the amount of energy available to do work, when we want to do work with a chemical, like, I don't know, burning something in your car's fuel tank to make the car go, the actual energy that does the work is the Gibbs energy, because when you burn gasoline, you're making a bunch of gas, so there's an entropy change as well as an enthalpy change. So we have to take these into account when we do proper chemical reactions, proper thermochemistry. And one of the big things about this is that here in red, processes are only spontaneous when the Gibbs free energy change is negative. Gibbs free energy change is negative. And this is the reaction that helps you figure out the Gibbs free energy change. It's the heat change, the endothermic or exothermic, minus the entropy change times the temperature. The T is the temperature. So the entropy change affects the Gibbs free energy based on the temperature of the system, which is why some processes are always spontaneous, but other processes are only spontaneous at certain temperatures. The classic example is freezing. This water, right, this liquid water, if it were to freeze into ice, that would be an exothermic system, right? Because the heat would have to come out. It would have to first cool down to 0 degrees and then freeze into ice. Both of those processes release heat. The delta H is always negative. So it's exothermic. It's going to release energy. You'd think that that would mean that it would be spontaneous. But because it's going from a liquid to a solid, and a solid is more organized than a liquid, we have an increase in entropy. Um, and so the increase in entropy kind of cancels out and overrides the decrease in enthalpy. It's annoying that those sound so similar. The increase in disorder overrides the decrease in heat. So even though it's exothermic, it is not what we call exergonic at room temperature. And so it won't proceed spontaneously. But if it gets cold enough, this T term gets small, gets low. And so T times delta S, the change in entropy, gets small. And then that negative heat from the water turning into ice does become negative, or it stays negative, but it's big enough to override the T delta S. And that so happens to be 0 degrees Celsius, that the temperature where that happens. This T is actually in Kelvin, so it's 273 Kelvin, but the idea is there. And then when delta G goes negative, it becomes a spontaneous process. It's exergonic. And same thing happens with boiling. Boiling is endothermic, so we kind of predict that it might never happen, but boiling represents an increase in entropy. And so when the temperature gets hot enough, 100 degrees Celsius, the increase in entropy overrides the increase in enthalpy. So the increase in disorder overrides the decrease in energy, overrides the increase in energy. And the boiling of the water at temperatures above 100 degrees is actually driven by the entropy release, the entropy increase, rather than the thermal energy, which is kind of cool. But again, keep in mind, we're not going to really talk about it or do it in our calculations. We're not using this formula in any meaningful way. I just want to talk about it in terms of some things are endothermic and spontaneous, and other things are exothermic and spontaneous. And it depends on whether they're endergonic or exergonic. We're not going to be dealing with these effects. In our simplified calculations, we're going to keep T constant, and we're going to not even bother thinking about delta S at all. So just the change in Gibbs is going to be approximately equal to the change in thermal energy in our simplified course. But just be aware, they're simplified. It gets more complicated when we get to higher level chemistry. Okay, next up, we're talking about bond energies. So I'm going to pause and set that up. All right, so this is bond energy theory. Bond energy theory, it's very simply stated that breaking bonds usually requires energy, and making bonds usually releases energy. And we're talking about free energy. Another way to say it, breaking bonds requires an input of energy, making bonds releases energy. This shouldn't be very controversial. Like the things are bonded, the chemical is bonded because it's a lower energy state. If it wasn't a lower energy state, they wouldn't have any reason to be bonded in the first place. They would rather be separate atoms. So it's easy to remember if you just keep that in mind. Like they're bonded for a reason, and they're bonded because being bonded is a lower energy state than being separate. Hence, breaking that bond, taking it from this bonded state out to two individual atoms, is going to require an input of energy. And when they go back to bonding, even if it's with a different chemical, it's going to release energy. And so the theory of bond energy says that the energy change in a reaction comes from the balance of the bonds you make and the bonds you break. Here's an example of a single displacement reaction. We see that X and AB, and then at the end XA and B. XA and B. So A is kind of hopping over to X. In order to hop over to X, though, this AB bond has to break. The AB bond has to break, and then the XA bond has to get formed. And this is tracking the energy, potential energy here. Down here we have something called reaction coordinate. So this is important when we talk about potential energy diagrams. It's not time, it's progress of the reaction. So you never really get a half and half kind of thing. It's kind of boom, boom, boom. It's very quick on individual reactions. So we can't really talk about time. It's reaction coordinate. Yeah. And another thing to talk about is this, the transition state. It's in square brackets, and it represents the highest energy state. It represents the time when everything is by itself. So it takes energy to break the AB bond. We're going to release energy making the XA bond, but somewhere in the middle, XA and B are in this weird high energy state as the bond transfers from one to the other. And it can kind of be analogous to each of the three atoms just by itself, because that's the highest energy state we can kind of think of as a transition state. So high energy state, it's assumed to exist at the moment of the reaction and no other time. And so it's very, very short-lived. Here's an example of one from an organic reaction. This is an addition, adding bromine to ethene. When we talked about it during the organic unit, we said that one bromine goes on each carbon, but it doesn't happen in one step. That would take too much energy to do it in one step. What happens is this double bond kind of half breaks, and ends up, you get one bromine on one side, and then you end up with this, the intermediate. This is a carbocation with a positively charged carbon. Very quickly, the second bromine will come in and attach to it. You end up with your final state. But this does exist. We can prove it exists in chemical reactions by looking at the stereochemistry. For example, when we do one of these, we notice if we do it in a ring that the bromines are always opposite each other. They never go up on the same side of the ring. On the ring, they always go opposite each other. And that suggests to us that the carbocation, generates on the opposite side of the bromine. So we have this proof of transition states and intermediates, but no direct, imaging, no direct confirmation that they exist aside from our models. But that's the transition state. It's a short-lived, high-energy state that's in the middle of the reaction. Here it is up here, the transition state. Very, very, very shortly lived. And it's short-lived because it's at the top of the peak. From the transition state, you could either go back down to X and AB, or you can fall all the way down to XA and B. Reactions are sometimes reversible. You can go both ways. So here is something interesting. This is a news story from 2015. It's a University of Ottawa professor, so a little bit of Canadian content for us. This is Dr. Paul Corkum. He's from the U of O, and he's working on very, 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 very short duration lasers, attosecond laser pulses. And the theory goes that you could use these extremely short pulses, like a flash, like a camera flash, to catch a chemical in the transition state and actually image the transition state. This is considered, very important in chemistry. If we could actually get a picture, a real physical evidence of the transition state, would be very cool. And it put him on the short list for the 2015 Nobel Prize in Physics. So he was like one of 18 possibilities to get a Nobel Prize in physics. He didn't get it in the end, but it was cool he was on the short list. And then we did actually have a Canadian physicist who did get a Nobel Prize, and she was also a laser physicist in 2018, Donna Strickland from Waterloo. And here she is accepting her Nobel Prize from the King of Sweden. Very, very cool. That we have some cool high-end laser physics happening in Canada, and potentially it could be used to actually image the transition state. I think that's neat. Okay, so talk about bond energies. Once again, here's another example of it. Here's the cellular respiration equation. Here we've got glucose and oxygen. Here we've got carbon dioxide and water. We have to break bonds before we can make bonds. We break carbon and hydrogen bonds, carbon and oxygen bonds, oxygen bonds, and it takes energy to do it. Right? This is made out of mostly glucose, the cellulose in my paper, but it's not on fire right now because there's not enough energy to break those first bonds. If I bring something hot near it, suddenly things will move faster because that's what thermal energy is, and then the things can come in with enough energy to break those first bonds and start the whole process. And then because it's exothermic, you make more heat, and then that heat promotes the reaction. So that's this activation energy here. Activation energy is kind of the energy needed to break the first bonds, ish. And then this is the bonds you're making. It turns out that CO2, the carbon-oxygen double bond in CO2, is very, very, very strong. It's a very low energy molecule because of the strong bonds. And so when we make CO2, we tend to release a lot of energy because making bonds releases free energy. And so a lot of processes that we rely on to give us a lot of energy end up making CO2, and it's becoming a bit of an environmental issue. And the downside of this is in order to go back, right? In order to go back, we have to put in a bunch of energy to take the CO2 and turn it back into glucose. We'd have to put in a bunch of energy. And of course, trees and plants and stuff do that all the time. They take CO2, they turn it into glucose. They use the energy from the sun to do it. Yeah. In this case, the products have less potential energy than the reactants. And you can tell because they end up down here and these guys start over here. And so here's delta H, change in potential energy, negative delta H, so it's exothermic. And here's a bond energy table. So we're going to get into a bond energy practice problem. Bond energy practice problem. Okay, let's do a bond energy practice problem. So you can track it. You can track the bond energy and predict delta H by tracking what you make and what you break. It doesn't give you a perfect answer for the heat of the reaction because of those entropic effects, the entropy effects. So you can do this bond energy thing and then look it up, and then it's a little bit different, but that's because it'll happen with different conditions and things like that. But here's some bond energies in kilojoules per mole of those bonds. And you see hydrogen, 432 kilojoules per mole, nitrogen, 160 kilojoules per mole, all kinds of different ones, carbon, oxygen. Oxygen single bond is very low. Oxygen double bond is pretty high, but not too high. The carbon-oxygen double bond, 745 kilojoules per mole, but in CO2, which is what this is down here, it is 799 kilojoules per mole. So that's a bond energy table, and you get all these different ones. One of the strong ones is the nitrogen-nitrogen triple bond, which is why nitrogen is so hard to process. It's 78% of the air, and it's very, very hard to break apart. You learn all kinds of interesting things in a bond energy table. But what we're interested in is using these bond energies to predict a enthalpy change. So here I have water. Water splitting to H2 and O2. And I've balanced it already just because I felt like balancing it. And we need to balance it in order to see how many bonds we're actually making and how many bonds we're actually breaking. This is going to require an input of energy, but we can prove it with the bond energy table. So what are we breaking? We are breaking OH bonds. That's the bonds that we're breaking. We're breaking 4 of them. So let's just write that down here. Break. Ooh, that's too big. Okay, break 4 times OH bond. All right, so let's find out how much that is. An OH bond, let's find it on our table. OH, there we go. OH single bond. OH single bond, 467 kilojoules. It requires 467 kilojoules of energy. Each. Right, each per mole of energy each. So total is 467 kilojoules times 4 because we're breaking 4 bonds. 1, 2, 3, 4. It's whatever that's going to be. 4, 6, 7 times 4. 1868. So plus 1868 kilojoules, because that's the energy we're putting in, right? Let's look at our make. Right, let's actually make this red because we're breaking it. Let's see what we're making, and we'll make that green because we're making them. All right, let's make that green. We're making a hydrogen-hydrogen bond, another hydrogen-hydrogen bond, and an oxygen-oxygen double bond. So we have to watch out for that. We have to look at the oxygen-oxygen double bond. We're going to make 2 times hydrogen-hydrogen bond, single bond, 1 times oxygen-oxygen double bond. And we need those energies. So the hydrogen-hydrogen bond, if I go back to my table, is the first one in the table, 432. 432 kilojoules per mole. And we're making an oxygen-oxygen bond, which is, let's see, oxygen-oxygen double bond. We want that double bond. So it'll be over here on the double bonds, multiple bonds. Oxygen-oxygen, 495. 495 kilojoules. Right, and this will be, so we figure out our bond energy by putting those together. 402 kilojoules times 2, because we're doing it twice, making 2 of them, 1, 2, plus 495 kilojoules, 95 kilojoules, is equal to, let's see how much that is, 432 times 2, 432 times 2 plus 495, 1359, 1359 kilojoules. And it's a minus. We're releasing that energy. Right? We're releasing that energy. Right? And then the total, right? The total here is going to be, the total, we are putting in 1,868 kilojoules. Take away what we're releasing, 1359, we're releasing that much. Kilojoules equals whatever that's going to be. 1868 minus 1359 plus 509 plus 509 kilojoules per mole, per mole. So per mole of this reaction, we have to put in 509 kilojoules per mole. In this case, breaking the bonds is higher energy than making the bonds. We have to put in more energy than making the bonds. So that's a practice problem. That's how you do one of these. You have to figure out which bonds you're breaking and which bonds you're making. Knowing how to do the structures is very important there, which is why we did structures in Unit 1. And yeah, that's that. Here's an example for methane, where we take CH4 and O2, and we're making CO2 and H2O. And we have a more complicated, more complicated thing. 4 CH bonds, 2 oxygen-oxygen double bonds. That's what we're breaking. The total that we're making, 2 carbon-oxygen double bonds, but they're the special carbon dioxide ones, so 799 kilojoules. And we're making 4 hydrogen-oxygen bonds for the 467, the same bonds. And we're making that much, and so the delta H here is actually negative. We're releasing energy. We're making more energy than we need to break the first bonds. Note that a lot of that just comes from the 2 CO2s. It's so much energy released when you make a CO2. Yeah. All right, that's the thing. Let's talk about understanding potential energy diagrams. Yeah, last piece is understanding these diagrams. We've kind of been reviewing it over the course of this lesson, so hopefully this won't be a long session. The big thing to keep in mind is that the delta H, which is diagrammed here, here's delta H, is only start point to end point. Start point to end point. It doesn't matter what's happening along this section. It's only start point and end point. That's going to get very important when we talk about Hess's law next week. but the activation energy does depend on process. So we can actually change the activation energy if we, I don't know, put in a catalyst, or we do it in multiple steps, right? Or do something else. We can have a different kind of bump. You have different activation energies. You could even go like multiple steps. That's a bad multiple step thing, actually. It's like, you could do something like this, which is actually what your body does. It processes glucose in multiple steps. But the delta H is not going to change. Start point, end point. So delta H is not going to change, but because of bond energies, because of this thing we just talked about, bond energies, because you're still breaking these bonds, making these bonds, but the activation energy can. And also, you can go backwards, right? You can take CO2 and H2O, plants do this, and then you turn it back into glucose, and it just reverses, makes the delta H positive instead of negative in this case. But the activation energy, right? The activation energy for the reverse process is very high. You have to go all the way up this hill before you can fall down the other side. So activation energy will change forwards and backwards, but delta H will just flip signs, positive to negative. And that's part of it. Reactions have this activation energy. Sometimes the activation energy is very, 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 very low. But it's usually present. And it's usually the energy required to kind of break the first bond or weaken the first bond or something like that. There are certain types of reactions where you don't have to break a bond to make the first bond. You just have to overcome some electric repulsion. Classic example is a substitution, certain types of substitution in organic chemistry. SN2 reaction, if you want to look it up. It's called a back attack. The thing that's substituted in literally comes in and hits the chemical, and then something flies off. It's like those Newton's cradle things, basically. It's a very cool one-step process. To draw these things, one good hint is to start the reactants in the middle. That way you have room to go down or to go up. This is an exothermic reaction, right? It's coming, the products are lower and the delta H is here. If it was endothermic, you could still have a bump, you just end up higher. So this is why starting in the middle kind of helps. You can go up or down to show an endothermic or an exothermic reaction. The other big thing to keep in mind, reaction coordinate. It's not time, it's just reaction coordinate, or sometimes reaction progress. So yeah, it's not based on time, it's just left side, right side, and then the activation energy and the transition state up here. So there's the transition state up here. Right. We don't necessarily know what the transition state is, but we know what the activation energy of a reaction is if we do enough thermochemistry with it to figure out, what's the minimum temperature for it to go and things like that. We can make it happen. I think that's it for this. That is. So let's do a review. We talked about enthalpy, entropy, and Gibbs free energy to explain why certain exothermic reactions are not spontaneous. For example, the freezing of water, which is exothermic but is not currently happening because it's like 20 degrees in my room, which is because there's a decrease in entropy even though there's an increase in thermal energy of the surroundings. Then we talk about bond energies, that breaking bonds requires energy, making bonds releases energy, and that comes from the fact that this is higher energy than this for pretty much every chemical system. This is high energy, this is low energy. So going from this to this is an input of energy, going from this to this is a release of energy. We did a practice problem with the water, bond energy practice problem. You are definitely going to get a bond energy problem on a test, so please learn how to do that. It's also useful for your thermochem lab. And then we did some potential energy diagrams and talked about how to understand them, how to interpret them, how to find delta H on one, how to find activation energy on one, and some hints about drawing them, in that you start your reactants in the middle and you write reaction coordinate or reaction progress at the bottom instead of time, because it's not time. I see that so often, and I really wanted to harp on that. Well, that's just about 30 minutes, so I'm going to finish the video there. Thanks for paying attention, and I'll see you guys in class.